So welcome back, Level 3 physicists, continuing on with the electronic standard, and today looking at electromagnetic induction. So remembering from last year the right-hand rules, okay, so the right-hand grip rule, thumb points in the direction of the current, the fingers are the direction of the field lines of the magnetic field, and then we have the other right-hand grip rule. This time the fingers point in the direction of the current, okay, and the thumb points in the other direction of the north pole of a electromagnet or an electromagnet. We also have the third right-hand rule, where this time the thumb points in the direction of the current, the fingers point in the direction of the magnetic field line, and the palm points this time in the direction of the force, okay. And how do we represent the direction of the perpendicular to the page? Well, into the paper is going to be a cross, and out of the paper will be a dot. In terms of electromagnetic induction, it can go both ways. So basically, electric motors convert electrical energy into kinetic energy, whereas electric generators convert kinetic energy into electrical energy. And these are a couple of examples here, the top one being a motor and the bottom one being a generator. So the other point is around magnetic flux density. Okay, so the magnetic field strength is basically the flux density, okay, capital B, and basically it's the magnetic flux divided by the area. Okay, so it's how many magnetic field lines pass through a particular area, okay. And in order to have electromagnetic induction, you have to have the field lines being at right angles to the loop, okay, so max flux. And if it's in parallel, there'll be no flux given. In terms of electromagnetic induction, basically what happens there is a wire moves steadily at a speed at 90 degrees to the magnetic field, okay, through these magnetic flux. At a certain time will generate a EMF. Okay, so EMF equals the change in the magnetic flux divided by time. So you can change that by either moving the magnetic field or moving the wire, the conducting wire. Flux linkage. So usually we're not just dealing with one wire, we deal with coils made of loops of wires. And that will be N times phi, which will equal N times B times A. So number of turns in that wire to make those loops times the magnetic flux equals the number of turns times the magnetic field strength in Tesla divided by the area of the uniform magnetic field. Okay, so and flux, of course, is in Webers. So then we have the fourth right-hand rule. Okay, so that's going to be the thumb this time points in the direction of the motion, and the fingers point in the direction of the field lines, and this time the palm now points in the direction of the current that's being induced. Okay, and again, representing it, if it's going into the paper, it will be a cross, and out of the paper, just like you see in the diagram, it will be a circle. And in terms of the induction, the creation of this voltage, it basically is created by a conductor in three ways. So either you move the conductor or the loop or the coil through the magnetic field, okay, and that's what you're doing when you're generating electricity. You either move, or you could move the magnetic field over the conductor, okay, so you can have the magnets actually rotating. Or you vary the strength of the magnetic field, this time by changing the current from direct current to alternating current, where the current goes back and forth. Okay, so the current cannot be created when the coil is completely out of the magnetic field, as the current cancels out. Okay, so this is basically a loop moving from point I to II to III, and you'll see on the right-hand side the associated voltages on that. So basically, the voltage is at a maximum in point I, because the current's only going in one direction, because the wire on the left-hand side isn't in the magnetic field. In the middle, the current and the loops are going to be opposite directions, so they'll cancel out, so there'll be no voltage. And on the right-hand side, there will be a maximum voltage, this time in the negative, because only one side of the loop is actually in the magnetic field generating current. Then we get to Lenz's law. Okay, so Lenz's law becomes more important in the next lesson, actually, as well. So basically, when current flows, the direction of the current will oppose the change in flux that is produced. Okay, so you can see that in the diagrams there. Basically, an inducting coil will create its own magnetic field as magnetic passes through it, and that magnetic field will be in opposition to that of the original magnetic field that's moving through it or away from it, so either in or out. So if it's moving in, it's going to increase the strength. Moving away, it'll decrease the strength of the field as it moves away, but the currents will be in opposite direction to that that will be induced through Lenz's law. What does this mean? Okay, so that means that a change in magnetic field, the magnetic flux, an induced EMF can be expressed as thus. So it's going to be a change in flux over the change in time. It's negative this time because it's going to be induced. It's known as a back EMF, and we'll look at that more in the next lesson. And the conductor has two ends as it moves through the constant magnetic field, and therefore, if you have a coil and a number of turns times the change in flux divided by change in time will give the associated EMF. And for a generator, which is rotating, then the EMF will be equal to the magnetic field strength times the area of that loop times the number of turns times omega, the rotational velocity. And in terms of generators, as seen in the previous slide, the EMF will be magnetic field strength times the area times the number of turns of the loop times the rotational velocity. Therefore, the effect of increasing the speed of the rotation of that coil, or potentially the rotation of the magnet over a stationary coil, increases the rate at which the magnetic field is being cut, increases the maximum EMF, and also the frequency of that EMF will also increase.